Thank you for that lovely introduction. And I wanted to start today with letting you all just ponder a question. What's the scariest thing you've ever seen in code? For me, it's this comment. This should never happen. Now, we all know that engineers use this comment to capture some state that seemed impossible given system constraints and what they knew at the time. Often it's an error code they never thought would be returned, or it's something they thought wouldn't be null that is in fact null. And the fact that they never expected it to happen means they couldn't reason about when or why it could happen, which means they didn't think through the consequences and probably didn't test the code all that well. And so years later, someone changes the code, and that error is just finally returned maybe. And suddenly the thing that could never happen happens, and we get to see how the whole system reacts. I've been on the receiving end of many pages generated when the impossible suddenly became the inevitable. So whenever I see that in code, I think, just wait. And so, as Laura introduced me, I'm Michelle Brush. I am a site reliability engineer like most of you. And then I do have responsibility for the reliability of Google Compute Engine and persistent disk. When people ask me what my job is who aren't in tech, I say my job is to worry. And that I worry about how things might fail. And then when they fail, because they always do, I show up and get them working again. And then we try to learn from what just happened. And the one thing I've learned responding to incidents is that every line of code has the potential to be load-bearing. And this is because every line of code carries all of the assumptions that the engineer made when they wrote it. And even if those assumptions were absolutely correct on the day the code was written, of course things change. And this to me is why things like design reviews, launch reviews, production readiness reviews, and even code reviews can only take us so far in terms of reliability. They are point-in-time reviews based on how the system is expected to look right now, and then the system changes. And part of being a good SRE is understanding the nature of change. In the systems we support, every microsecond something is changing, right? And we cannot control those changes, even if we want to. And so all we can do is build systems that are easy to change, that recover quickly when a change fails, and that do not require that we understand and review every change in the system. And now our jobs are changing. Large language models have made it so people can build applications, refactor large code bases, add features and fix bugs in less time than before. And of course, the SRE in me worries, right? That's worrisome. But I'm also excited, and I'm hoping through this talk I can make you feel excited about it too. However, to get you there, I'm going to walk through a bunch of ideas. Some of them you've heard before, but please bear with me. I'll pull them all together. To start, as the guiding thought experiment, let's imagine what happens if agents do make the work of building and running software faster, easier, cheaper, better, all those things. And what if we suddenly had all the programmers we ever wanted to build whatever we wanted once we figured out what that was? What would we think would happen? My hypothesis is we're about to experience the Jevons paradox. The Jevons paradox says that if something becomes cheaper or easy to do, we do more of it. As a great example, I take way more pictures now that I don't have to carry around film and get it developed, right? So if we think of the capacity to do engineering work as a limited resource, which it has been for a long time, and the act of coding and doing commands and operational work, it all gets easier and faster. The Jevons paradox suggests that the world is going to engineer more things. Software applications that we never thought possible will be built now, and things that were previously too expensive to even consider will now be cost effective. We just can't imagine what all those things are right now. And so as software gets cheaper and easier to build, we will come up with more ways to use it and bring it into our lives. And that already happened through the years as we moved beyond different levels of abstraction in software. And the good news is these new systems will create demand for engineers. Now, as a result of all this, we are still going to need software engineers and site reliability engineers to help design these new applications, to make sure they're reliable, to keep them running. But some of the work we all used to do will now be taken away and automated by the use of agents. That's probably happening. And so what does it mean for us to be less exposed to the day-to-day coding and operations as we gradually automate away part, but not all of our jobs? Well, the best framing for this is the paper, The Ironies of Automation. And I'm sure many of you are familiar with it, but I'll quickly summarize. What Bainbridge tells us is that when you automate away most of a task that a human used to do, but leave some of the work left for humans, the overall job requires even more skill. Part of this is because what you've left for humans is the work that requires judgment, like you couldn't just write it as rules or heuristics or patterns. But also, the automation itself creates a whole new set of tasks that have to happen. You have to monitor the automation. You have to fix it when it breaks. You need to account for it failing or making mistakes. And that is all harder than doing the original work in the first place. And making things worse, because you weren't doing the work anymore, you've automated away, you lose familiarity with it. And this is called skills decay. And so when something breaks, it takes more time for you to understand and sort of like page back in the memory of how to do the work and what it should look like. And so basically, as you remove some but not all of the work, the job gets harder, not easier. And you need more people with more skills, not fewer. To illustrate with a very simple example, let's take dishwashers. We have dishwashers. They've taken away most of the work of washing dishes for us, but they still left a few things for us to do. Basically, even automating this simple task left us things like we have to now detect when the dishwasher is done. We now have to check each dish because sometimes the dishes don't all get clean. And then when they don't get clean, we have to troubleshoot. You know, was the water not hot enough? Was there not enough pressure? Do we need to clean the filter? And this troubleshooting is harder than just washing the dishes. But also, when the dishwasher breaks, suddenly we have to start doing this activity we haven't done in a while, and we're not as efficient at it as we would be if we were doing it every day. However, we still want to use the dishwasher, right? Like, even though it introduces these challenges, because it does save us time, and to be honest, we didn't really enjoy the work of washing the dishes anyway. So basically, when we think about what's happening in our industry right now, our relationships with the systems we support is going to change. But we'll still need to respond when something goes wrong. So even though we'll be less familiar with some of the work we used to do, we'll still have to jump in and fix things. And so the big question is, how are we going to respond to failures when we know we won't have people who fully understand the system anymore? They won't have the depth. Now, if you're an engineering leader and you're in this audience and you take nothing from this talk, I want you to remember this slide, which is basically the Jevons paradox suggests that we're going to be building a lot more things once programming is easier, faster, cheaper. And the ironies automations say that we're going to need more skilled engineers to review the outputs and monitor the system that works and fix it when it breaks. And this means in all likelihood we're going to see more demand for skilled engineers over time, not less. And the important question, though, is what skills are we talking about? Well, definitely debugging and troubleshooting, that's obvious. I love this old Brian Kernighan quote. However, even this quote assumes you wrote the code you're debugging. And even now, especially as SREs, most of the time we're debugging code that is a mix of something maybe we wrote and a lot of what somebody else wrote. And now we'll have code that the large language model wrote in the mix. Now, I want to be clear, this is not an AI/ML talk. I'm not going to go into detail about deploying models or running systems or how to keep GPUs and TPUs healthy. I am going to talk, as promised, about managing complex systems, but we have to talk about AI/ML right now to understand how our jobs are going to change. And I have one more concept before I'll jump into that, which is something called the curse of knowledge. The curse of knowledge is a very simple model for human knowledge. It has two dimensions. The first dimension is competence. Are you incompetent or competent at a subject? The second dimension is consciousness. Are you aware of your level of competence? And in particular, can you explain it? I want to be clear that incompetent in this context is not an insult. It's just we're all incompetent at something in life, right? I'm aware that I suck at basketball. I'm really bad at it. I used to write medical software, so I know enough about medicine to annoy doctors. And I definitely know how to cook a chicken. Now, if you take this two-dimensional model and you stack it like a pyramid, at the bottom are all the things that we don't know. And let's be honest, this is most human knowledge, right? We all have just a slice of what we understand. And for those things, we are unconsciously incompetent. And this is a dangerous place to be if you're overconfident, because that's how we get Dunning-Kruger. Part of learning is moving beyond the state up to this conscious incompetence part, where you actually are aware that you don't know things. And because you're aware you don't know things, you become willing to learn. And as you study something, eventually you become competent at it, and you are aware of your competence. You know why you know the things you know, and that makes you a really good teacher. You can explain it. However, we all know that if you do something enough, eventually you move up into this unconscious competence place, where we start working more on intuition. Like we have these heuristics and we have these feelings and we operate based on those feelings. And when we get there, it's really hard to explain why we think the things we think or why we feel the things we feel to someone else, because we've just created all these mental shortcuts. And if you're an experienced engineer, I bet there are times when you found yourself looking at a design document or an architecture diagram and you thought, this is wrong. This is so wrong. But then when somebody asked you why, you struggled to put it to words, right? That's your unconscious competence speaking to you. And it makes you sometimes a bad mentor because you can't really teach people who aren't there yet because you can't explain it. And when that happens, you end up being the one person who has to show up all the time and fix things because you're the only person who understands the things the way you do. And that leads me to my next point, which is in our jobs, things break a lot. You know, obviously software has bugs, hardware fails, you know, processes fall apart. And when these things happen, we have to make use of our intuition built on years of experience to point us in the direction of what might be wrong. But often it's not until we've really dug into the problem and understood what was going on that we can actually figure out how to fix it. And so our jobs constantly require us to move between this unconscious and conscious competence to do our job all day long. And so the mental framing that works for me is to think that generally speaking, large language models are by their nature unconsciously competent. They know things, they know a lot of things, but they can't explain why. Humans were much better at the conscious competence part. We're also really good at knowing what we don't know. LLMs are not. The way you think about hallucinations is that there are moments when AI/ML is unconsciously incompetent and it doesn't know what it doesn't know, so it gets creative and fills in the blanks, right? Now, obviously, the various models are getting better and better at getting rid of hallucinations, and there's a Hugging Face is a cool leaderboard you can check out. When I made this slide, the top model was a 1.3% hallucination rate. However, some were as much as like 10%. And often when I talk about this, people sometimes say things like, well, it feels worse to me. Like when I'm working with these models, I can't believe it's 1.3% or 10%. And my answer to that is that this benchmark that they use basically tracks whether or not the answer the model gave was in the source material or where they made up something that wasn't in the source material. And so when you think about our jobs, we're often asking the models to solve novel problems for us. There is no source material. And so we're asking them to be creative. And that's part of the feature, but it also means that what we get is a little more unpredictable. And basically, because of that, a lot of working with agents and models is going to be about making sure that they produce the right thing in the first place. And that has always been the hardest part about our jobs. It's not building things or running things, but knowing what is the right thing to build or how to keep something running the correct way. So put this all together, at our fingertips, we can now call up a number of like coding or operations agents who will behave like really solid but overconfident engineers. And if we want them to produce quality systems, we're going to need to give good instructions, of course. We'll have to monitor their work. We may have to jump in and make sense of the system when they do something wrong and try to figure out how to get it working again. Maybe we'll create guardrails around what they do, right, to make sure that they don't run off and do something like delete the whole database. And when they make mistakes, we will have to give them feedback and ask them to correct their mistakes. And of course, there'll always be tough decisions about which parts do we trust them to do versus we keep for ourselves. And this job overall is harder than doing the original work, right? But like the dishwasher example, we'll still want to use these tools because one, will be more efficient, and two, they'll probably do some work we didn't like doing anyway. Now, some of you might be thinking this sounds like being a tech lead, and I kind of think it is. It's kind of like being a tech lead, but you have this seemingly unbounded supply of engineers. So what's going to happen? Well, what is going to happen is that because these agents and the models are not rate limited by the words per minute they can type, they're rate limited by the speed of inference and our ability to give them feedback and good instructions. What I imagine is that our systems are going to change at a rate we've never seen before. And that means they're going to get bigger and they're going to get more complex. And so we're going to have to figure out how to deal with these increasingly complex systems. And unfortunately, complexity theory tells us that as systems get more and more complex, their behavior becomes emergent, And it's harder to understand cause and effect, meaning it's harder to understand ahead of time the consequence of the change you're about to make, but it's also harder to look at in hindsight about why did this thing just happen. And all the moving parts and assumptions almost begin to behave in a way that feels non-deterministic, maybe even chaotic, right? And this happens even if your system is described as a simple algorithm or function. Chaos theory has a ton of examples of like really simple functions that can have extreme results and extreme variability based on just slight differences in inputs. So we're going to be living with more complexity going forward. And we're going to have to figure out what to do with that. And of course, you can't talk about complex systems unless you talk about How Complex Systems Fail by Dr. Richard Cook. And if you haven't read the whole thing, please do, because I don't have time to go into all of it. But I'm going to speed through what I think is the most relevant takeaway. And I tend to do this visually. And how I think about it is I think all systems start as a small system that mostly works. And I say mostly because things are broken all the time. And also, I say small, but in reality, a small system that works involves usually multiple services, sometimes a data store, but definitely people that interact with the system following policies and using interfaces. And working with these complex systems requires that we acknowledge that the system is this mix of humans, hardware, and code, and that all the participants are interacting while making assumptions. And the assumptions and the interactions make the system complex, but that complex is almost like an aura around the system. We can't actually see it, and the boundaries are kind of fuzzy. And this is because a lot of assumptions are implicit and undocumented. And also there's variation in system performance, right? And that complexity is often the cause of incidents. We've all had the experience of an outage happening even when everything was working as intended, right? Because it's the bad assumptions amongst the parts that create the circumstances that allowed for some small change to trigger the outage. Maybe something started running a little slower. Maybe that error code we never thought was going to return finally gets returned. And that breaks an assumption somewhere in the system, and of course, things cascade. And of course, we, SREs, and other humans are the source of resilience, and we respond and we resolve the issues in that complexity. And we get the system working again, and maybe we remove some of the bad assumptions or behavior that led to the outage. But also in an effort to prevent similar outages, we add controls, we add automation, and that all helps, but it also makes the system bigger and more complex. And so now we have a new set of assumptions and behaviors to manage, even bigger than the initial set. And complexity increases as the system grows. And again, we have some outages. Maybe it's a hardware failure, and humans have to show up and fix the issue. And maybe they add more safeguards and controls. And the system gets bigger and more complex, with even more hidden assumptions. And if we're using AI/ML to build parts of the system, the speed of change is just going to make this explode, right? It's going to accelerate. And we'll be managing these increasingly complex systems. And of course, going back to the ironies of automation, because we automated away some of the work when we did this, some of it will feel like a black box to us. Like we won't understand all the working details anymore, and we'll have to adjust our approaches. Now, when I talk about this, sometimes the first answer I hear is, we'll use AI ops. And I do think that is part of the answer, but let's just be frank, that's just a bigger system. And one that also behaves non-deterministically, so it'll be more complex than the original system. And so we need additional answers. And to reiterate my statement from earlier, any line of code can be load-bearing, so even the code or commands written by LLMs can cause an outage, of course. So if agents only make a few mistakes for, say, like 1,000 activities, the rate that they are producing code will still generate many hidden surprises, just as humans already do, but faster. And while we'll have tests and code reviews, some things inevitably will be missed, and then they'll come back and poke us, like needles hiding in a big haystack. But of course, making things challenging, since we're going to be dealing with complex systems, there's going to be a lot of parts. And so in some sense, it's more like needles hiding in many haystacks. And since most outages have multiple contributing factors, of course, any one of these haystacks can be part of the problem. So how do we find all the needles? We can't rely on human review, because that's going to be too slow. And also, traditionally, human review only catches obvious errors. We can get better at testing, and I will talk about that. But let's start with the idea we're going to have to change how we approach addressing issues in the system, fundamentally. Because back to the curse of knowledge, we're going to have that harder time moving between that unconscious competence and conscious competence to understand what went wrong. And of course, as Kernahan said, debugging was already harder than writing code in the first place. So I think we're going to have to embrace that our relationship with the system and how we understand it will be more abstract. It's just changing in that way. And that's okay, because we've been doing this our whole careers, right? Like, the tech industry has a long history of increasing levels of abstraction. We're not writing code out of AND and OR gates anymore, thankfully. We're not even using assembly language. And we've gotten to the point now that often when we talk about systems, we talk in these whole constructs, like the database, or the API, or this particular service. And we've always been moving in a way that we got to abstract away bigger and bigger parts of our solutions. And this is going to accelerate. And I think what's going to happen is we're going to move to the top of this table, right, to the top of this stack. And we'll be spending more of our time thinking about systems, processes, and people. And this means the way we respond to incidents and breakages will be less about understanding exactly what went wrong and more thinking about the problem as a systems problem. And when I think about viewing systems, I always think about this old paper called the 4+1 View of Software Architecture. It's a really great paper about how our systems have always looked different depending on who was looking at it. Like, I always used to joke about if you take two people to a whiteboard and you ask them to draw the same system, the pictures will look different. And that's actually an interesting conversation to have, is like, why did you draw that box and not that box? But this old paper said it wasn't just that. It's also that who you're talking to views the system differently based on what they work with every day. And so if you have your average developer, they think in the logical view, which is what the code looks like: functions, classes, APIs, if statements, for loops. And then you have, if you're someone who runs the deployments and the rollouts, you might think of the development view, which is how the system is packaged up: libraries, binaries, rollouts. And then if you're operating the system and responding to incidents, you might think about the process view, which is how the system runs and communicates in real time. And then if you're someone who's like deep in the infrastructure, you might be focused on the physical view, which is where is everything running? Like, which machines, which data centers, what is the power redundancy? But in the middle, there's always been this unifying experience of what is the user experience under different scenarios. And so moving into this abstract world, we first have to recognize these views have always existed, and we have to be aware of them all, because this is the full complexity of our system. But we also have to spend more time in that middle, reasoning about the user experience, what scenarios are going to happen, and how we want the user experience to feel when those scenarios happen. And when I mean scenarios, it's both a mix of positive things and negative things, like failure events, but also as the user interacts with various user journeys. And so I think more of our jobs will be about worrying, but in a way that we're asking what if at this level. And we'll have to start incorporating understanding how engineers, users, operators, and agents will be constantly changing this system. And that will change the way we think about our roles and what work SRE needs to do. And basically, we need a broader understanding of the system from not just how it lives, but how it was built, and what was involved, and what assumptions were made. Now, as a great way where we already do this in our jobs is that we already deal with the fact that when we're responding in incidents, we can't always understand what went wrong when we need to respond. And so we build generic mitigations, which Google thinks of this as a series of buttons or levers that we can safely push to get the system working right again, just long enough for us to understand the things better and actually get a more solid solution. The way I think about it is that there's a million ways anything can go wrong, so you need a few things you can just do to get them going well again. And all of you have done a generic mitigation, whether you know it or not, every single person in this room. And you've all done the same one at least once, which is turn it off and turn it back on again. That fixes all sorts of problems, right? Deadlocks, memory leaks, tons of problems. And that's a great one if your system's designed to support it, right? You have to have an architecture that supports it. Another obvious one is rolling back to the last working version of the software. It's an easy one we do a lot. But also things like if you suspect the hardware is the issue, back to that physical view, draining away from the hardware or triggering a live migration is another generic mitigation. And I think these will become more important because as we're less in the weeds of the system going forward, we're going to need more of these tools, and we're going to need to ensure that they work because it's going to take longer to page back in all the information about how the system works when we're responding. And so imagine we did show up and we did perform some generic mitigation, whether we drained away traffic or turned it off and back on again. And now we have to learn and fix some of the bad assumptions that led to the outage, right? And so the question is where to start. We have to focus our efforts somewhere, right? Maybe not. How about everywhere? I'm half joking, but since complex systems break our understanding of cause and effect, and because the relationship with the code has changed, we're not going to be as quick in terms of like reproducing the issue and doing some deep debugging. And so it'll be harder to understand exactly what went wrong. And so what we can do easily, though, is treat anything that could have gone wrong as a risk and then remediate those risks. By that I mean we no longer ever anoint a root cause, and instead we need to create mechanisms by which the things that are wrong can be continuously fixed. And the good news is we will now have a small army of operations leads to do our bidding in this regard. Recently, one of my SREs suspected there was a deadlock in a particular service that was contributing to the outage, so he asked an agent to find it, and it did. And then he asked the agent to fix it, and it did. Another engineer I know asked the agent to write more unit tests to catch edge cases, and that uncovered areas that needed to be fixed and likely contributing to what the behavior we were seeing. So we can have agents both find and fix things, but not even just the immediate thing. Recently, we had an outage exacerbated because a playbook had outdated commands, and we realized that we needed to not just fix this one playbook, but go look across the whole organization and see if anyone else had these outdated commands. And so we asked agents to do it, and they fixed them all at once. So another way to look at this is we have this opportunity to realize Linus's law finally, because we'll have enough eyeballs. And so the way I want to think about this is we often see a lot of patterns that contribute to outages, right? Bad error handling is my #1 contributor whenever I look at systems. But there's also concurrency issues, there's resource management challenges, and all of these are sort of patterns that you can see in the system, and they show up all over the place. And these are all the needles hiding in the haystack. And so the way we can bring reliability to the systems now using these new tools is we can basically say, what anti-patterns do we see in our systems? And can we pose them as questions about the code base? So for example, we've asked agents to find missing error retries, or where we have retries without back off and jitter. And then they can find those things for us. And this all comes back to this idea that reliability, and also just generally software quality, is a function of us all understanding that there are always going to be errors in the system, and that we all write bugs, and that, too, the number of errors or bugs is proportional to the size and complexity of the system, right? As the system gets bigger, there's going to be more of them. And the secret to great engineering isn't being satisfied just because the tests pass. It's being satisfied when you find enough things that are wrong. And enough is often built on your prior experience, so that's sometimes often your unconscious competence. So we take a systems thinking perspective. We can create a great feedback loop for ratcheting up system reliability by using these new tools at our disposal and basically ask them to find and fix enough bugs constantly throughout the system. And this will be a leading indicator of system quality. It's also a funny way to move between that unconscious competence of knowing that we'll have some problems in the system and the conscious competence required to find and fix them, with the irony being we're using the unconscious competence of the coding agents to help us here. Putting this together, imagine as a thought experiment, never having to manage a bug backlog. Now, obviously, we're not here, and we may never get here, but I like this as a guiding light, that we want to get to spend less time figuring out the right thing to fix and more time just fixing everything we can. And if a bug can be fixed, tested, and reviewed like in an hour, does it really matter that it's not the most important bug to fix? It's still a risk in the system because every line of code is load-bearing, and many low-priority bugs turn out to be contributing factors in outages later. At Google, we even commemorate this moment by having an I told you so badge, where if someone logs a bug and that bug is later identified as a contributing factor, you get to celebrate. So all of this to say, we get to rethink how we approach prioritization. And I think this will be a noticeable shift, and it'll be hard for some folks to adjust to. Because many of us have been conditioned to think that we always need to be working on the most important thing we can do for some definition of important. But if we can find things we need to do quickly and do as much of them as we can quickly, then it doesn't matter as much anymore. And this takes me to my favorite book on software development, The Art of Business Value by Mark Schwartz. In it, Mark talks about how one of the challenges we have in any engineering organization is assessing the value of the work we could be doing. And this is particularly challenging because we always have many, many great ideas about what we could be doing, and that always outpaces the capacity we have to do work, right? And this often creates frustration in the organization because this mismatch of the cost of doing work is so much slower than the cost of coming up with work that good ideas get starved for attention, right? You get a lot of those I told you so badges. And we don't know how to reason about the work we should be doing because the backlog gets too big and there's just too much to analyze. And then unfortunately, organizational politics start playing more of a role in what work we choose to do, right? And so the usual solution to this problem is like, oh, we'll just sort the backlog by value. And maybe we even go further and say, we'll use return on investment or cost of delay or some other way of assessing the importance of doing work. Maybe you get a stack ranking from your leadership. However, we have to realize that all of this sorting work also takes engineering capacity, because often you're asked to estimate feasibility, value, and the cost, right? So it's not free. And Mark Schwartz and others have pointed out that we're all bad at predicting both the cost and value of the work we want to do. And so when we prioritize based on these concepts, we're making decisions based on poor estimates. I think we've all had at least one project run double the original estimate or to turn out to deliver nowhere near the value we thought it would when we started. And the only time we ever truly know the value and cost of something is after we've built and deployed it. And so no amount of planning can ever fully fix this, and of course planning has a cost. However, we feel we have to prioritize by something because we do have a constrained set of engineering capacity, and we want that capacity working on the most valuable things. And Mark Schwartz proposed a path forward. One is to break things up into smaller, more easily delivered pieces. And two, make sure you're getting feedback from reality early and often. And this creates the opportunity to fail fast if your idea isn't working, right? And then you get to try more good ideas because you're not spending all your time on ones that aren't working. And I think this is another place that these new tools can help us. As the Jevons paradox suggests, we can build more things because building got more efficient. And so it'll be faster to test even seemingly, ridiculous ideas or absurd ideas. We can still test them quickly. And so the good news, experimentation just got a lot cheaper. And even better news is experimentation is the mechanism by which we manage increasingly complex systems. Because predictability is not a feature of complex systems, we often have to treat the work we do as a learning process when working with them. Because we can't predict the full behavior of the system. We can't devise a plan that just goes like, do A, B, C, and D, and everything will be fine. We often have to discover the work. And so this world coming to us, rigid plans won't work all that well. And we'll have to structure our work as a series of experiments that'll each inform each step of the plan, and we'll have to preserve optionality. And if we act this way, if we treat our work as experimentation, we'll be much more successful at containing the complexity. And when I say experiments, I mean in the most fundamental sense, which is we treat every project as a hypothesis about what we expect to happen when we implement it. And we cut up the project into mini projects so we can see if our hypotheses are correct more quickly. And of course, the good news is it'll be less expensive to do from an implementation standpoint. But the bad news is we still have to do the hard work of devising the experiments and driving the work forward based on what we learn. And for some of you, you're probably thinking that sounds like agile development, and it's similar in practice. Like agile development is one flavor of doing this. But this is more about reordering your work so that you answer the important questions first. Like you get the risks settled early and often. For example, you might do an upfront scalability test on the skeleton architecture before any business logic is implemented to make sure it will scale. Or you might actually build your capacity plan ahead of implementation based on back of the envelope estimates to make sure that you can actually afford to run the system once it's built. And the thing is, when you do this, when you plan based on learning, the project's going to proceed non-linearly. And that means you're not going to have this perfect Gantt chart, right, that just flows. And you're not going to have this perfect burn down of work either. It's going to look a little different. And this might make some people uncomfortable. Because the mistake engineering leaders often make is they demand a predictable approach when dealing with a complex system. and they don't empower their teams to work in a way that yields discovery. And I think this happens when you have an engineering-led organization where the people who wrote that first small system that works are now the leadership. But as you grow in leadership, obviously you're removed from the details. And so you spend less time there and you don't understand how complex the system's gotten. And so without even knowing it, these engineering leaders trick themselves into thinking you can solve problems the way they did in simpler times with detailed plans and best practices. However, the system you're dealing with will be this system. It's complex, maybe even chaotic, and you're gonna have to structure your work to account for that complexity and accept that some of the things you might try might fail. Because this system cannot be tamed with playbooks and best practices. It requires risk management, experimentation, and discovery. And if the system is really complex, you can no longer trust that you know the full set of system behaviors, and you can only suspect certain patterns of behaviors. And so to actually do your work, you almost have to probe or poke at the system a little bit and see how it reacts, right? What if I try this, back to those scenarios. And devising these experiments and exercises and doing them safely is not intuitive. It's a skill you have to build. In some ways, basically what I'm talking about is building feedback loops. And this is part of what SRE's always done, right? Like if you think about SLOs and error budgets, that was just a really clean and simple feedback loop on development velocity. And so we're gonna be doing this more. But because of the rate of change, coming back to how I started this talk, our jobs are going to be less about being the human feedback loop and being more about building feedback loops that scale with the rate of change. And the one way that works really well in my mind to think about this, about how do we build feedback loops at scale, is this concept called an architectural fitness function. An architectural fitness function is basically a system-level assertion for some of your system requirements. And I say system requirements, I mean the things we want to be true about the system regardless of what features it supports, right? SLOs are a great example of a fitness function. Another way of looking at them is they are a system-level mechanism for making sure the things that should never happen actually don't happen. However, they can also ensure the things that should happen still happen. And basically, you take these assertions and you codify them in a form of continuous testing, or maybe you enforce them architecturally by failing certain changes that don't meet your rules. And that ensures as the system changes, no matter how fast as the changes is happening, some things will always be true. So as a great example, one of the rules we have in Compute Engine is that the system should support an arbitrary number of clusters, and that clusters should be able to be added or removed with no side effects. You should just be able to not impact anywhere else in the system. And so how do we ensure this always happens, no matter what changes any human or agent makes? Well, we set up continuous automation that constantly creates, registers new clusters, then hides them and tears them down again, just over and over and over again. And that way we can prove that, or at least we can never prove, but we can catch the moment that someone makes a change that breaks this system requirement. The cool thing is this automation turned out to be a potential generic mitigation as well. Because one way to fix something is to safely delete it and recreate it, right? If you know you can do that because you're doing it all the time, then it's safe to do it. And this takes me to a key point. You have to treat your generic mitigations as system requirements. This means you don't just test when you change the mitigation tool. So if you don't just test your rollback system when you change the rollback system, you have to test those mitigations every time the system changes. So you should be constantly rolling back just to make sure it still works again. Other fitness function examples, you might say the system should support multiple operating systems. Maybe it needs to survive losing a certain number of machines. Maybe it should be able to handle a certain frequency of live migrations. You might make rules about your dependencies, like it shouldn't have any circular dependencies or some dependencies aren't allowed. Or you might say it can't crash during user interaction. That last one is one we had at one of the consumer device companies I worked for, where basically we had this testing apparatus we called the hopper, and it would randomly touch pixels until it eventually accidentally triggered a UI event. And then it would keep doing that over and over and over again, and all the event handling code would get triggered. And basically, before you could deploy your code, regardless of whether you changed the UI or not, you had to let it run in the hopper. And if it crashed, You would get the core dump, of course, and then you'd get the list of events that have been triggered. And it was really cool because we found all sorts of weird and improbable bugs in the system, and we were able to fix them before they created a bigger problem or before they impacted the user. And while, of course, this never proved that the software wouldn't crash, that would be impossible, we knew we were finding enough bugs, right? And if you do have agents or, that's weird. Okay, well, if you do have agents or other AI/ML in your systems, you have to accept that you're going to have to test those as a fitness function as well, right? And typically how people do that is they do that through the form of evals. So these are auto raters, these are manual raters, and I really apologize that my computer decided to crash. I always joke computers are a mistake when it does this stuff. So you want to test the evals work too. Now, oh, it went from the beginning. Hold on, sorry. Now, where I was going to say next is that the good news is some things about our job aren't changing. And in particular, what isn't changing is we are still going to be the people that need to show up and respond when things fail and get things working again. And I think if you are currently on call, you will probably still be on call. Just maybe the way you respond and the things you respond to will be different. And this is because, again, humans are the things that resolve the complexity, that resolve the challenges at that boundary of complexity. But hopefully, with everything you see coming at you with these agents, like, you'll be able to build tools that makes that job easier. And so ultimately, that's why I'm hopeful. I started out this talk like I worry, but I'm excited. I think SREs are used to dealing with complex systems. The problems they present are challenging, but also fun. And we're used to having to work with code we didn't really write and sometimes don't fully understand, right? That's just part of our jobs. And so to me, it feels like our skills in particular and our experiences will be critical in this new landscape. And that's why I'm excited. I think it's a great time to be an SRE. All right, thank you.